Hello there, folks. With me is my cowboy assistant Ulysses to help with some more demonstrations in conservation of angular momentum. So this little principle works on how we change the moment of inertia of an object, that is the mass. As we bring mass towards our axis of rotation, our spin increases and we spin faster and faster. This is what stars do. As they collapse and bring their mass inwards, they spin faster. All right, are you ready, Yuli?
Yep.
Are you ready for some science trooping?
Yep.
Okay, let's go. Let's show some spin. Faster, slower. More moment of inertia, less. More, less. More, less. Awesome. You want to do that one more time for us? Less, more. Less, more. Less, more. Awesome. It's all about conserving angular momentum. And as long as you have a freely rotating stool and you don't have external torques added in, you could do this demo at home and get a little good exercise while you're at it. All right, thumbs up. Thank you for watching. Hello there, physics curiosos and science students. We're going to do some demonstration today on moments of inertia, rotational mass, and we'll compare masses towards the center in rotation versus mass more outward in rotation. And we're going to do some demonstrations of that by my assistants, the Call Science Boys, Ulysses and Seth, and they are going to demonstrate how moments of inertia work with flips. Seth is going to do 2 different flips. That was a back flip. Seth, can you show us a front flip that is curled up into a tight ball so your moment of inertia is towards the central axis?
Yeah.
Oh, wow, that was fast. So
Wait, let me try doing it.
Seth had a lot of his mass towards the central axis of rotation, and that resulted in a very fast spin. Great job, Seth. Okay, now let's go ahead and extend some of your mass outward and see how much slower that is so we could compare. Wow, yeah, that's a lot more floppy. It slowed you down, didn't it, Seth? All right.
Me not land it.
Now our next demonstration is by Ulysses, and he's going to show us first a tight ball backflip. That was great. Okay, then he's going to do a not so tight ball backflip. So his rotational mass is extended out. Whoa, much slower. Great comparison. Okay, guys, let's show us a really nice. Let's do your fastest rotation. Curl up really into a tight ball as much as possible. Nice. Okay, Seth, your turn, and we'll call this a success. Great job, Call Science Boy assistants. Those are some great demonstration in moments of inertia. We might be familiar with the spinning ice skater when her arms are inward, how much faster she could twirl versus she or he versus not. All right, thank you, Callboys. Hello there, physics folks. With me is my assistant, Ulysses, one of my cowboy science assistants, to help show some awesome angular momentum demonstrations again. And we're going to do the standard spinning wheel demo. So we have Yuli here getting the wheel a spinning, and he's getting a good spin on it so that he can show you how angular momentum is conserved here. So we have the wheel spinning in one direction. Okay, so with our thumbs we go this way, angular momentum points up. Now what happens when he changes the direction of the angular momentum. He starts a spinning on the stool. What's happening is, to keep angular momentum conserved, the stool does a double spin to add up to the opposite initial spin of the wheel so that it equals the initial angular momentum. Yes, that's it in a nutshell. Lots of numbers there, but angular momentum is always conserved. You want to try that one more time for us? Give us another quick demo. Let's take it for a spin again. I should say he's a spinning. Only the wheel. Total system spin, only the wheel. And thank you so much, our assistant Ulysses. That was a great, fantastic job. And to finish up our little segment, here is the key idea behind what he just showed us. That's right, the initial angular momentum is a spinning wheel, and the final angular momentum is the opposite angular momentum of the spinning wheel initially, plus 2 times the initial angular momentum of the spinning wheel, which is in the spinning chair system. All righty, and that's it for today. Keep on spinning. All right, so what we have here is a standard spinning top. And we have forces acting on that top. It has mass, so we have gravity acting on it. It has a normal force upward, but it's on its axis rotation, so that doesn't contribute to torque. However, there is torque generated by gravity acting on its center of mass. And what that ends up doing is creating a little precession. That's when it starts to fall to the side towards the direction of its torque. So we know the top has angular momentum depending on which way it's spinning. So in this case, it's spinning in that direction. The angular momentum is pointing upward. And the torque, by Newton's second law, is a change in the angular momentum over time. So the torque is changing its angular momentum, and you see it's precessing more and more, and it finally falls over. Nice. One more spin. That one wasn't so good, but here we go. It's starting to wobble or precess, and you could get the precessional values from knowing the numbers, the mass, the axis rotation, etc. Next up, we have this rattleback right here, and these are really interesting. So if you look at the shape, there's a little change in its geometry. It's not perfectly symmetrical, so that will result in an interesting sort of spin. So I spin it one way and it starts spinning backwards. So we spin it this way, it wobbles and begins to spin backwards. So it has to do with the geometry and the way the center of mass is acting, the way gravity is acting on its rotational axis. So it's an uneven amount. So hence the torque is going to produce this reverse spin. Very interesting object. Now let's move on to your more typical demo. This is a gyroscope. Okay, so we know that if we try to stand this gyroscope, it'll just flop over like that. Why? Because it wouldn't be in equilibrium. It has too much gravity acting off center of mass. So we can't balance the center of mass here. So what we do know is that if we could get this spinning, so if I get this gyroscope spinning, it'll stay in balance a bit. There we go. Okay, so again, we got two forces. We got the normal force pointing upward from the pivot, but it's not going to produce a torque because it's on the axis of rotation. And then we have the center of mass. We have gravity acting on the center of mass, which is producing this torque again that is going to be in the direction of this precession. So what happens is, if I do this again, let's get another spin on here. The torque is acting to change its angular momentum, again by Newton's second law. So we have that slowly beginning to wobble, the precession. And that's because the torque from gravity is acting on it. So the torque is changing the angular momentum. Now, a really interesting feature of gyroscopes, if you were out in space and let's say you wanted to change the direction of your spacecraft, what you do is you get the gyroscope to spin in one direction. So you get the gyroscope spinning in one direction, and then the spacecraft will begin rotating in the opposite direction to conserve angular momentum. Very interesting feature, and that's how we're able to maneuver spacecraft and get them to go in a different direction. So one last spin here. Lots of wonderful physics to keep your head spinning here. Okay, let's go. And this is a feature throughout the universe. We see it with planets spinning and torques acting by the gravity of other masses pulling on them. So it eventually leads to a sort of precession in the rotation, a change in the rotation. So any change in rotation is related to angular momentum. All right, keep on spinning.